All right, so this is chapter 13, which is going to talk all about liquids. And then the really important part of this chapter comes towards the end, where we're going to talk about intermolecular forces, which are the attraction forces between different molecules. And so before we get started, we're going to think about some different properties that we see in liquids. And these properties are different based on what type of liquid we have because of the molecules that we have. So the first property of liquids would be called surface tension. And surface tension is that resistance of a liquid to increase its surface area. So if we think about water, for example, water has a fairly high surface tension. If you look at the water bug down there at the bottom, that water bug is able to stand on the water because water has high surface tension, meaning that the surface of that water does not want to change its area. And another way to think about that is the forces to keep those water molecules close together is fairly strong, and so you don't want to break that surface. This all become or because of cohesion, and cohesion is the attraction between the same type of molecule. The way I always remember that is co. The prefix co represents together, or like coworkers is the same type of thing. So cohesion is the same type of molecule. And water, again, exhibits a very high surface tension due to hydrogen bonding, which we'll talk about later. The other type of attraction is an adhesive attraction, or an adhesive force, and that's the attraction between different types of particles. And the way I always think about this is like glue. Glue sticks two pieces of things together. So adhesion is the attraction between a liquid and another substance. And so there's two different examples here. You've got a bottle of wine, and if we spill that up, we can clean that up with a piece of paper towel, and that's because we have an attractive adhesive force between the water molecules and the paper. And then we also have what's called a meniscus in tubing, and the meniscus is because of the attraction between the in this case, it's water on the right and mercury on the left, but the water on the right has an attractive adhesive force between the water and the glass tubing. And so that's why you kind of see that dimple in the tubing, especially when we start to get into lab. So there are 6 different phase changes. We're really going to focus on the 4 in the middle. The 2 on the top and bottom are not super common, but I do want to talk about them. So sublimation is the process of going directly from a solid into a gas. And a great example of this would be dry ice. If you've ever used dry ice or seen it, it comes to us in a very cold block. And then it instead of melting into a liquid like a normal block of ice would, it turns into carbon dioxide gas, and then that just floats away once we open up the container. Deposition is the opposite, so it's going directly from a gas into a solid, skipping over that liquid phase. And frost in the winter or the spring or whatever is a great example of deposition. The water vapor in the air freezes directly to another substance, and it skips over that liquid phase. So it's water vapor in the atmosphere going directly to ice as frost. So we're going to focus on the other 4 in the middle there a little bit more as we go through this. The first one that we're going to talk about is evaporation. Evaporation is sometimes also called vaporization or boiling. And evaporation happens when liquid molecules have enough energy to leave the liquid phase into the gas phase. And so if we leave a substance out in an open container long enough, eventually your volume is going to disappear. And that's because no matter what conditions we have, for the most part, any liquid that we have is going to have some of those particles jumping out of the liquid phase into the gas phase and going off into the atmosphere. And so down there in the bottom right, you can see that most of the particles are staying in the liquid phase, but we do have a few that get enough energy to shoot out of the liquid phase into the gas phase. Now, the property that we study with evaporation is vapor pressure, and vapor pressure is a measurement within a closed container. So we've got to have some sort of container with a top to it so that these particles aren't just constantly disappearing into the atmosphere and not going, and they're not, going off randomly and not able to come back. So the reason we need a closed container is because we need the rate, or another word for rate would be like speed or the amount of particles. So we need the rate of vaporization or evaporation, whichever way you look at it. That needs to equal the rate of condensation. And condensation is when the liquid comes back, or the gas comes back into the liquid phase. And so um, the point at which we measure vapor pressure is when the number of particles going into the gaseous phase are the same number of particles that are coming back into the liquid phase. And so down in the bottom right, you can see kind of an image there. There are particles going up into the gaseous phase, but there are also particles coming back down into the liquid phase. And so that's when we're going to measure the vapor pressure. This is the picture that I like the most for vapor pressure. It really helps describe what's happening. And so we place a liquid within a closed container. In this case, it's kind of this U-shaped container. But the thing we really care about there is that pressure gauge. And so what happens is a liquid with no gas on top of it really doesn't exhibit any vapor pressure at all. But over time, we know that any liquid is going to have some of its particles go up into the gaseous phase. We're going to let that continue on until that equilibrium is reached. And when I say equilibrium, I just mean that the number of gaseous particles going back into liquid is the same as liquid going into gas. So we have the same number of particles going from one phase into the other, or vice versa. And so at that point, we can measure the vapor pressure. And that vapor pressure is, again, the pressure that the gas is exerting onto a pressure gauge. Usually that's how we're going to measure that. But essentially, it's just the amount of liquid that's able to escape into the gas phase. So the higher the vapor pressure, that means that we have a more volatile liquid. And volatile just means that you have a lot more evaporation of the liquid particles. And so when we have a more volatile liquid, that is because there is less attraction between the liquid particles to keep them in the liquid phase. So a liquid with a high vapor pressure means that those particles aren't able to hold together to stay in the liquid phase as well. And so the particles go into the gaseous phase, producing a lot of that pressure. We also have boiling point, and boiling point is the temperature at which vapor pressure is equal to the external pressure. And so external pressure, we're really thinking a lot of times of that atmospheric pressure. The normal boiling point of water at 760 torr, or 1 atmosphere, is 100 degrees Celsius. And the normal boiling point obviously is going to be different for different liquids. Normal boiling point is just at that normal atmospheric pressure. Normal atmospheric pressure is typically defined as 760 torr, or 1 atmosphere. So what does that mean in terms of different situations or different applications? Well, at a higher altitude, there's less pressure above any substance in the atmosphere because we're up higher. And so if we're up higher and there's less air above us, that means the atmospheric pressure, or the pressure pushing down on us from the air above us, is lower. And so with a lower external pressure, that means that our liquid is going to be able to boil at a lower temperature. However, a lower boiling point means that the attraction between the liquid molecules is lower. So if we've got water and we've got gasoline and we've got, let's say, motor oil, all three of those substances have different properties. And so gasoline in that case would have the lowest boiling point because the attraction between the molecules is the lowest. So we can use what's called a vapor pressure curve, and what this does here is this graphs the temperature at which a substance boils to the external pressure, and in this case it's millimeters of mercury, which is the same as torr. And so on this graph, it's nice for us. It graphs that 760 line for us. That's the normal boiling point. And then it also tells us what temperature that happens at. So if you take a look at the red line, diethyl ether, that one has a very low boiling point, only about 34.6 degrees Celsius. So it would start to boil at a relatively low boiling point. Ethyl alcohol, which is ethanol or drinking alcohol, that has a boiling point at around 78. And water is pretty extremely high for a liquid. That has a boiling point of around 100. So what we can do is we can actually use this graph to trace back to the pressure line. to figure out if we have a temperature of a certain degree and we want to figure out the boiling point, we can figure that out. Or if we know the pressure and we want to figure out the boiling point, we can go that way. So let's say that I'm trying to figure out the boiling point of ethyl or diethyl ether at 600 torr, or millimeters of mercury. And so what I'm going to do here is I'm going to draw my line over from 600, hit that line, take it down, obviously trying to go as straight as possible, and figuring out what that temperature is. So 30 degrees would be somewhere like here. I would say that's probably around 26 degrees Celsius. So that's how you use one of these graphs. You can go over from the pressure and go down to the temperature, or you can go up from the temperature and down to the pressure. Okay, so we're going to practice some of these problems. You can use the graph on the right to figure out the boiling point of ethyl alcohol at 1,000 millimeters. You'll figure out the boiling point of water at 600 millimeters of mercury, and then you'll figure out the pressure when the boiling point of diethyl ether is 20 degrees Celsius. So again, use those lines, draw from what we know to what we're trying to find, and then give us that answer. Pause and work through this. All right, so let's go through the answers. Number 1, boiling point of ethyl alcohol at 1,000 millimeters of mercury. So what I'm going to do here is I'm going to go across. I'm up here at 1,000 millimeters of mercury. I'm going to go across till I hit my ethyl alcohol line. I'm going to come down here. Oops, trying to draw as straight as I can. And I'm going to get right there. I would say that answer there is probably around 85 degrees Celsius. Again, you have a little bit of a room to figure out your answer. It wouldn't be exactly 85, but as long as you're close to 85, I'd accept that. Now let's figure out the boiling point of water at 600 millimeters of mercury. So I'm going to go over from 600 millimeters of mercury. I'm going to hit my water line, and then I'm going to come down to grab, my temperature, sorry, a little straighter. And so I would say that there is probably around 80 or 95 degrees Celsius. If the normal boiling point of water is 100 degrees and we're at 60 millimeters of mercury, which is about 160 millimeters of mercury lower than normal, then our boiling point should be lower. And then the last one we're trying to figure out is the pressure when the boiling point of diethyl ether is 20 degrees Celsius. So this one's different. We got to go up from 20 degrees Celsius till we hit that line, and then we're going to come over. Now this one isn't as easy, I would say, to figure out this. 500 would probably be around here. So I would say maybe a good number here would be somewhere around like 525 millimeters of mercury. All right, so the last few things we have to talk about are melting and freezing points. So melting and freezing are the opposites of each other. Melting goes from a solid to a liquid, and freezing goes from a liquid back into a solid. So as a liquid releases heat or thermal energy, its particles start to slow down and solidify. So when we freeze, we're really releasing energy or thermal energy in the form of heat to the surroundings. Now, in a freezer, what's happening is that the surroundings are so cold that if we put in, let's say, room temperature water, what's happening is that the low temperature of the freezer is pulling that energy out of the water, which turns it into ice. And so the temperature at which this process of freezing and melting happens is called the melting or freezing point. And water's melting or freezing point is 0 degrees Celsius. It's the same temperature. It's just depending on, are we melting, which is solid, to a liquid, or are we freezing, going from a liquid to a solid? The other last thing we have to talk about is density of liquid. So density is defined as the amount of mass in a given volume. And so the lower the density, the higher it would be in a mixture. The low density substances are going to rise to the top because there is less mass in that volume. And so if we think about some different applications of this, ice floats on water because ice is less dense than water. It's one of the few instances where a solid is less dense than its liquid form. And we can be pretty thankful for this because we, here in Wisconsin, are able to enjoy a little bit of ice fishing in the winter. Another prime example of density of liquids would be oil and water. Oil is less dense than water, and so that's why it's going to be on the top of the mixture. So you can always just remember lower density, higher in the liquid. They're kind of opposites of each other. Now we're going to get into the big topic of this unit, which is intermolecular forces. The intermolecular forces really depend or determine a lot of the different functions of a liquid and what their properties are like. So an intermolecular force, or IMF, you're going to hear me use the term IMF a lot. That just represents intermolecular force. And those forces are the attraction between molecules of the same substance. So in a container of water, the intermolecular forces are the forces that want to keep those water molecules attracted together. There are going to be 3 intermolecular forces that we're going to discuss, and this list here is from weakest to strongest. So we're going to talk about dispersion forces. Now, please note that when you are reading this in your textbook, or if you look at your homework or different other applications, you're going to see it be called London dispersion forces. I prefer to just call it dispersion forces, but a lot of other documents or things you might see out there refer to them as London dispersion forces. They're the exact same thing. It's just 2 different names. Exact same thing. One just adds the word London in there. The next will be dipole forces, and the third and most strong is a hydrogen bond. So dispersion forces, again, these are sometimes called London dispersion forces. These are the forces that are present in every single molecule. So all substances, polar or nonpolar, have dispersion forces. And the reason for this is because we have what are called instantaneous dipoles. So let's break that word down. Instantaneous, meaning at any given snapshot in time, these dipoles exist. Well, what's a dipole? A dipole, if you remember back to electronegativity and polarity, a substance that has a difference in electronegativity has a dipole, and a dipole just means that part of the molecule is positive and part of the molecule is partially negative. Well, in any given molecule, these instantaneous dipoles come from the fact that electrons are constantly shifting in their cloud. And so in one given snapshot of time, the electrons might be one place, which gives that area a partial, very, very partial negative. And then in another snapshot of time, the electrons might shift. And so that area now has a very partial negative charge. And so these very, very slight positive and negative charges attract to one another, and those dipoles are constantly changing. So if we take a look at the top right, it's kind of tough to tell, but that more purplish cloud behind represents the electrons. And so the electrons are constantly changing. The nuclei stay pretty much the same distance, the darker circles, but the purple in the background is constantly changing. And those constant changes form what we see down towards the bottom. So on the bottom, the blue side on each of those molecules would represent that the electrons are more over towards the right-hand side of each of those molecules. If they're over on the right-hand side, remember that electrons are negative, and so that shift in electrons to the right-hand side would give us a partial negative charge, leaving the other part of the molecule to be partially positive. And so the attractive force between the partial negative and partial positive is what attracts those particles together. Now, every single molecule, no matter how small it is, no matter how big it is, even atoms have dispersion forces. So if we think about things like neon gas, even though it's one atom that makes up that kind of that molecule or that cloud of electrons around that atom have a dispersion force. It's able to shift its electrons around in every single moment in time. So this is just kind of a visual representation of what those dispersion forces look like. Now, how can we make the strength of dispersion forces higher or lower? It's all dependent on the molar mass. So the heavier the molecules in atoms exhibit, the stronger the dispersion forces they have. So you can figure out the weight of molecules. I know we haven't technically talked about molar mass yet, but if you take a look at what makes up a molecule or what makes up an atom or what makes up a particle, we're really looking at the mass that you see on the periodic table, which is that decimal. And so if you add up all the masses for a molecule, let's say that we've got a carbon and, if we've got a carbon and 4 hydrogens. Carbon has a molar mass of around 12.01. And then we've got hydrogen, which is 1.01, but we've got 4 of those. So 12.01 plus 4.04 gives me around 16.04. That's how you kind of find that mass. Again, it should be pretty obvious just taking a look at what we're combining to figure this out. And so the reason for this is because larger atoms or molecules have a greater ability to have their electrons shift. There's more atoms and there's more electrons, which means that we can shift those electrons around further. And so that we get a greater positive and greater negative attractive force. So the next one, we have to review polarity a little bit. So we're done with dispersion forces. Dispersion forces are present in everything, and they get stronger with the bigger molecules. Now, polarity happens when two atoms bonded to each other have a large enough difference in electronegativity. And so if we think back to that electronegativity table, our fluorine up here in the corner is our highest, and then down here is technically francium. This is our lowest, and so electronegativity increases going up, and it increases going to the right. And so the atom with the higher electronegativity will be partially negative because the electrons are pulled towards that, and the atom with the lower electronegativity will be partially positive since the electrons spend less time around it. So if we think about something like HF, that, or I don't want to use that, sorry. Let's use HCl, my bad. So the Cl is more electronegative than the hydrogen, and so what's going to happen here is that the electrons are going to be pulled a little bit closer to chlorine. So what really looks like is they're still shared between them, but the electrons spend a lot more time around chlorine than they do around hydrogen. And so this chlorine is a little bit partially negative. That's what this little like and S sign means, is partial. So that's partially negative, and our hydrogen is partially positive. And so if we think about what this means in terms of kind of what we draw, is we draw this little positive arrow there. And so in order to figure out polarity, we have to know what those molecules look like. So this is why we learned about Lewis structures in the last unit, was because we need to be able to draw these structures and think about what they look like in order to figure out the polarity. So you can see here we've drawn water, and then that bottom one is ammonia. This arrow you're seeing here is called a dipole arrow. Okay, and what that means is that the positive part here means that that atom is partially positive, and then the end of the arrow up here means that this is partially negative. So we've got two partial positive areas, and then the oxygen area kind of has that partial negative. Now, I do want to point out here that the bond that students often kind of get mixed up on is this carbon to hydrogen. So if you have a carbon and hydrogen bond, we consider that bond to be nonpolar. So you have to have a difference in electronegativity that's greater than like 0.5. And so the more electronegative atom, the ones closer to fluorine, are going to be the ones that pull the electrons closer. And then the one that has less electronegativity doesn't have the electrons around it as much. So if we think about what this means in terms of polar versus nonpolar, in order for a molecule to be polar, there needs to be a polar bond. So if we take a look at these different examples, all the examples on the left have a polar bond. On the right, this nitrogen example, that is a total nonpolar molecule altogether because it's two of the same atoms that's nonpolar. In carbon to hydrogen, this is a polar bond, or we've got two polar bonds there, I should say. But it all has to do with the molecule's shape that allows it to be polar or nonpolar. So let's take a look at what that means here on the next slide. So if we have a molecule that has polar bonds and a lone pair of electrons on the central atom, then it is polar. So if we take a look here, we've got water and we've got ammonia down there at the bottom. So water and ammonia both have polar bonds, meaning that the oxygen and nitrogen are going to want to pull the electrons more than the hydrogen. If we take a look over at the right-hand side, those would be nonpolar. So that those lone pair of electrons change the shape, which allows the overall particle to be polar. And so you can see this bigger yellow arrow there. The bigger yellow arrow shows us the the polarity of the overall molecule. Those little black arrows show us the bond polarity, but the bigger yellow ones show us the overall polarity of that molecule. And so if we take a look at water and nitrogen, those lone pair of electrons are what give us that polarity. If we have one bond and it's more polar than the rest, then it is polar. So if we take a look at the top example, we've got that one bond. Chlorine is far more electronegative than hydrogen, and so the chlorine is going to want to pull those electrons, making it polar. If all the bonds are polar, but there is not a lone pair on the central atom, then the molecule is nonpolar. So let's take a look at these two examples over here on the right. On the right, we've got carbon and carbon and oxygen. The oxygens are more electronegative, but because those are in a straight line, it's like playing tug of war with the same opponent. So we've got two oxygens trying to pull the electrons with equal strength. And so because they're pulling in the same direction, or opposite directions, I should say, then that's considered nonpolar. The bonds themselves are polar, but the molecule overall is nonpolar. And then down here at the bottom, this is carbon tetrachloride. Each of these bonds is polar as well, but because they're all pulling in a equal direction from each other, then this is nonpolar. So if you can think about playing tug of war in a 3D kind of sense with all of the same opponents having the same strength, you're all trying to pull on that carbon atom, but because we're all pulling in equal directions and we're all pulling with equal force, the overall molecule does not have a polarity to it. So why do we care about polarity? Polarity really helps determine whether we have dipole-dipole attractions. So molecules that have a permanent dipole, which means molecules that are polar, display dipole-dipole attractions. And so in order to have dipole-dipole attractions, you have to be polar. If you aren't polar, then all you have is dispersion forces. But if you are polar, then you have dipole-dipole attractions. And these are stronger than dispersion forces. And so molecules next to each other line up so that those partial negatives of one molecule are going to line up with the partial positives of the other molecule. So this is what it kind of looks like. If we want to think about this, this could be something like HCl. And so we've got our H over here and our Cl here, H here, Cl here. And so remember that our chlorine is partially negative and our hydrogens are partially positive. And so we're going to see that attraction here between the partial positives and negatives that form that attraction. On the right-hand side, this is looking a little bit different, but it's the exact same thing. So our chloride would be up there and hydrogen down here. And then the opposite here, hydrogen and chlorine. And so that chlorine to hydrogen is going to form an attraction, and the hydrogen to chlorine down at the bottom is going to form an attraction. So that is how it looks when we bond these dipole attractions. Now, these dotted lines are showing attraction and not actual bonds. That's an important thing to notice. So those dotted lines that we draw when we put some molecules together, those are just attractions. They're not actual bonds with each other. So just to review this, you need to be a polar molecule to have dipole-dipole attractions. And dipole-dipole attractions are a step stronger than dispersion forces. So how can we increase the strength of a dipole-dipole attraction? the way we're going to do this is we're going to increase the dipole itself, meaning that we are going to try to make a larger difference in electronegativity. If we take a look at these three hydrogen halogen bonds, we've got hydrogen chloride, hydrogen bromide, and hydrogen iodide. Now, with these, what this means for us is that hydrogen chloride has the biggest electronegativity difference, and that's because it's highest up in that 17th column, which means it's most electronegative. So chlorine is able to pull on the electrons from hydrogen a lot better than the iodine can pull on the electrons from hydrogen. And because of that, you can hopefully see that these arrows are different sizes from one another, and that's on purpose. So the arrow for hydrogen chloride is bigger than bromide, which is bigger than iodide. And so our hydrogen chloride is going to have the greatest dipole-dipole attraction because it's the most polar molecule. The last one we're going to talk about is hydrogen bonding. And hydrogen bonding it sounds kind of odd. It's not an actual bond, it's just an attraction. But hydrogen bonding happens because it is a electronegativity difference between some different atoms. So hydrogen bonding is the strongest IMF. And what we need here is we need a hydrogen covalently bonded to one of the highly electronegative elements. So we need a hydrogen bonded to nitrogen, oxygen, or fluorine in order for us to see hydrogen bonding. So you need to see an HF, you need to see an H directly bonded to an O, or you need to see an H directly bonded to an N. You can't just have an O and an H in the formula and expect it to have hydrogen bonding. You need to actually have that H directly bonded to the O or the H directly bonded to the N. Now, HF is unique. There's only one combination, that is it. It's just HF. You can't have any other particles on there. So the H and the O and the H and the N have some more different variations, but HF is the straight up answer here. Now, hydrogen bonding is the strongest because we have those partial positives and partial negatives. The partial positive is always on the hydrogen, and the partial negative is on the fluorine, oxygen, or nitrogen. Now you can see here that these dotted lines represent the attraction between different water molecules. Please note that these are not actual bonds, they're just attractions or forces. And so what we do is we sometimes line up molecules to show how they would be attracted to one another. So another example of a polar molecule would be something like methanol. So methanol has carbon with 3 hydrogens coming off of it. Remember that those carbons to hydrogens there are nonpolar. And then we have an O and an H. And so to show attraction, what we might do here is we might draw another particle with an H, an O, and then that CH3. And then we'll draw those dotted lines here between the hydrogen and oxygens to show how those attract to each other. So that's how we actually visually see these attractions with each other. These are the strongest type of bond, and again, you need an HF, an O, and an H bonded to each other, or an N and an H bonded to each other. Now, how do we figure out which IMFs we have? Well, everything has dispersion forces. That is a given. In order to figure out the other ones, you got to think about what's actually happening with the molecules. If we have a hydrogen atom that is directly bonded to fluorine, oxygen, or nitrogen, then we have hydrogen bonding, and that's our strongest IMF. But if we don't have an H directly bonded to a oxygen, nitrogen, or fluorine, then we have to think about, is it polar? If it is polar, we have a dipole-dipole attraction. And so in order to figure out polarity, remember that we have to think about the bonds themselves, the atoms that are next to each other, but we also have to think about the shape. And in order to have a dipole-dipole, you have to have a polar shape to it. So let's practice some of these. Determine what the strongest IMF in each of the following examples is. Again, remember they all have dispersion, but some of these may have a more strong type of attraction. So pause, work on the problem, and then come back. All right, so if we take a look here and we think about how to draw our different Lewis dot structures, remember we have to add up the number of valence electrons first. So phosphorus has 5. Each fluorine has 7 times 3, which is 21. So we need 26 total electrons. Then we're going to draw our skeleton structure, P, F, F, F. That took up 6 electrons, so we need 20 left. And so I'm going to go 2, 4, 6, 8, 10, 12, 14, 16, 18. So 20 minus 18 is going to give me 2. Those 2 need to come on phosphorus. So if we take a look here, my phosphorus to fluorine, each of those bonds themselves are polar, and that's because fluorine is very electronegative and phosphorus isn't quite as electronegative. So each of these bonds has a dipole, and since we have that lone pair of electrons, that's going to mean that we kind of have this pyramid shape here with those fluorines pulling down. So all of those fluorines are pulling down, and so the overall polarity of this is going down. Since this doesn't have any H to F or H to O or H to N, it's not hydrogen bonding. All of them have dispersion, but because it is polar, we have dipole-dipole attractions for PF3. Now our next one is silicon tetrachloride. So silicon has 4. Our chlorides have 7 times 4, which gives us 28. 28 plus 4 gives us 32. So we're going to draw Si in the middle with chlorides coming out. That took up 8, so I need 24 more. 2, 4, 6, 20, 22, 24. So we don't have any more electrons that need to be placed. If we take a look here, each of these is polar, but because they are all pulling in the same direction, they're all playing tug of war with each other in the same direction, and they all have the same strength, then we have a nonpolar molecule. So each one of them, the bonds are polar, but overall the molecule is not polar because they're all playing tug of war with the same strength in the same direction. So this is nonpolar. We don't have any hydrogen even present there, so it can't be hydrogen bonding. This one just has the dispersion forces for our answer there. So dipole-dipole for 1, dispersions for 2. Now let's take a look at NHBr2. So N has 5, our H has 1. Each bromine has 7 times 2 gives us 14. 14 plus 6 gives us 20. So let's start to make this. It tells us that N is the central atom. So we need a hydrogen there. We need some bromides. Hydrogen does not get another electron. So we placed 6. We need 14 left. So 2, 4, 6, 8, 10, and 12 go on the bromines. 14 minus 12 gives me 2. That 2 needs to come up here on the nitrogen. So let's take a look here. The first thing I immediately see that sticks out is this N to H, okay? And if you see an N to H, an O to H, or an HF, you know that we have hydrogen bonding here. And so that's our answer. This is a polar molecule overall, but because our hydrogen is directly bonded to our N, our nitrogen, then we have hydrogen bonding. So number 1 is dipole-dipole, number 2 is dispersion, and number 3 is hydrogen bonding. So why do we care about this? Well, it all has to do with those properties we already talked about. So the liquid properties with IMFs, the stronger the IMF, the more the molecule wants to stay in the liquid phase. That's what we really need to think about. The stronger the IMF, the more attraction we have to keep that molecules in the liquid phase. And so if we think about the strength, remember dispersion is the weakest, dipole-dipole is in the middle, and hydrogen bonding is the strongest. So stronger IMFs lead to higher melting and boiling points. That's because those particles want to stay in the solid or liquid phase more than they want to go into the gas phase. It also means that we have a lower vapor pressure, and the reason for that is because if we have stronger IMFs, we want to stay in the liquid. We don't want to go into the gas phase. If there are less particles in the gas phase, then we have a lower pressure. And this also just generally leads to higher cohesion forces. So let's figure out some different strengths of these different examples. And so we're thinking about the first one, which has the highest boiling point, which has the highest vapor pressure, and which has the highest melting point. So pause, take a second to think about this. You really need to think about what type of IMFs they have and then how those strengths of IMFs change. If you forget about the strengths, feel free to go back in this PowerPoint. I talk about how to increase those strengths slightly throughout. All right, so in this first example, we're really looking at, okay, highest boiling point. To increase our boiling point, we need to increase IMF. So we're looking for what has our, not a P and F, which has our highest IMF out of those three. Well, if we take a look at these different substances, we've got H2O, and H2O looks a little something like this. Hopefully, right away, you notice that we have O to H bonds. We've got two of them. And so because of that, we have hydrogen bonding for H2O. CH4 looks something like this. Remember that our hydrogen to carbon bonds are nonpolar, so this is nonpolar. If we're nonpolar and we don't have O to H or N to H or H to F, then we have just dispersion. And then HCl here looks like that. HCl has a bond going, a polar bond between the hydrogen and the chlorine being more electronegative. And so this has dipole. Now we want the highest boiling point, so we want the highest IMF. So our water here would have the highest boiling point. And so if we take a look here, our ranking would be HCH4, HCl, and then H2O would be our rankings going from lowest to highest boiling point. Number two, which of the following would have the highest vapor pressure? Now, higher vapor pressure means that we have lower IMF. This is the opposite one. So higher vapor pressure means that a lot of our liquid particles are able to go into the gaseous phase. So for this one, we're looking for the lowest IMF. And so if we take a look here, we've got PI3, PF3, and PCl3. All of these are going to look the exact same. They're all going to look like this. PI3 with that lone pair, PF3 with that lone pair, and PCl3 with that lone pair. Now, all of these are going to have the 6 around them. I'm just not going to draw all of them. So if we take a look, they all have phosphorus as the central atom. They all have slightly polar bonds. But if we take a look, P to F is our greatest electronegativity difference. So this is the highest dipole. Chlorine is in the middle, and then over here on the left, P with our iodine, our phosphorus iodine, this is our lowest dipole. And we want the lowest IMF to give us the highest vapor pressure. So lowest IMF here would be our PI3. So our answer for this one is also the first answer. So PI3, phosphorus iodide, is our lowest dipole, which gives us our highest vapor pressure. And the last one, which of the following would have the highest melting point? Here we're looking at all diatomic molecules. And so if we take a look, in this case, diatomic molecules are all non-polar. And if they're all non-polar, that means that they only have dispersion forces. And if they only have dispersion forces, we're looking for highest molar mass to give us the highest IMF to give us the highest melting point. And so if we take a look, we're looking for the biggest molecule. Nitrogen is our smallest. This has a mass of around 28. Oxygen is next with around 32. Chlorine has around 70. And bromine has around 160-ish. So if we take a look here, we're looking for the highest mass. Highest mass will give us the highest melting point, and that would be bromine. And this actually works out if we think about the properties of the periodic table. Remember that bromine is a liquid, and all three of these are gases. And so at normal room temperature, bromine is a liquid because it has enough attractive forces to keep those molecules in the liquid phase and not in the gas phase.